Kia ora team, welcome to the online tutorial. Today we're going to be talking about angular momentum. Okay, so I'm going to start off by defining angular momentum and jumping into the equation. So rotational objects possess angular momentum in the same way that objects experience translational motion possess translational momentum. Okay, put simply, an object that is moving won't just stop. Okay, it has a little bit of oomph behind it. Now, we would give the equation to describe angular momentum with L being our angular momentum equals our inertia times our angular velocity. Okay, again, where L equals our angular momentum, okay, which is measured in kilogram meter squared per second. Okay, I is our rotational inertia. Okay, measured in kilogram meter squared. And omega, or lowercase omega, is our rotational velocity. And this is going to be measured in rads a second. Okay, radians per second. So, before we move on, I want to make a note, okay? And that is angular momentum, much like normal momentum, is conserved. Okay, discussing this, if we think back to primary school, probably when we thought we were real cool, you could throw a hula hoop forward while spinning it backward. Okay, and when it hit the ground, it would come back at you even though you threw it forward. Okay, this is a phenomenon that links to this momentum being conserved. Okay, always is conserved, and it's one of the key ideas they ask or that they require you to discuss or state as a assumption in NCA questions. Okay, no external forces, momentum is conserved, you can do your calculation. All right, so nothing too crazy here. We can see that angular momentum is dependent and proportional to both inertia and rotational velocity. Nothing too crazy there. Okay, we can see that if inertia changes, our velocity will change because our angular momentum is conserved. All right. An example they do for this often may be, and you're going to have to put up with my really terrible drawing skills here, I'm going to draw what I attempt to draw as a figure skater. Okay, imagine that's his little skate, pirouetting on the ice. Okay, rotating on the ice. Now, to do some kind of trick, our figure skater spreads his arm and his leg, or their leg, okay, and we get a pirouette. But mass distribution has changed. Okay. Now, from our previous video, we know when your mass distribution is less central to the center of rotation, you're going to get a greater inertia. So, if our momentum is conserved as it is, we're going to have a change in angular velocity. So, L equaling IW, or I omega, okay, if our momentum is conserved, so stays constant, our inertia has increased because we've got a less central mass distribution about the point of rotation, okay, our angular velocity must decrease. Okay, so this is a question, or not a particular question, but this is a concept they like to discuss or test you on in NCA, and that's just what happens to a rotating object when the mass distribution changes. Okay, we know that our rotational inertia is proportional to mass distribution or related to mass distribution. Okay, therefore it will change, it will increase as you get less centrally distributed, meaning when our angular momentum is conserved, our angular velocity must decrease to accommodate. Okay, so we could have an individual spinning really, really fast, they open their legs and arms out and they spin a little bit slower. Okay, so that's the basics. We can also link translational and angular momentum together, okay, through the equation. Oh, get rid of my red, sorry. L equals mvr. Okay, so if we have an object like a ball, a hula hoop example, rolling in a translational motion or rolling in a straight line, okay, we are also going to have angular momentum because that object is rotating, right? Where L equals, again, our angular momentum in kilogram meter squared per second, okay? M equals our mass, kilograms. V equals our velocity. And this will be translational. Okay, which is measured in meters a second. And R being our radius of our object, which is rotating, measured in meters. So radius, standard index unit, meters. Okay. So nothing too crazy here either. We can just see that an object with a mass and a velocity that is rotating is going to have an angular momentum, and we just times that by the radius. Okay, and again, the big takeaway is angular momentum is conserved. Okay, meaning that if you change the inertia by changing the distribution of mass from the center of rotation, you are going to affect our angular velocity, meaning if you spread things out, things are going to slow down. Okay, hopefully that's been helpful, team. Hopefully you can get out there and do some physics. Good luck.